6.1 day 2 starts off with another example of a discrete random variable. I'm going to leave this example to you, the one about North Carolina State University and their grade distributions. So you should be able to handle this example entirely, and that is on your own. One thing I do want to mention on this page, there is actually a formula for the mean, or the expected value as it's called. See, that's the notation for expected value, for a discrete random variable. And this is actually on the formula sheet. So it says the expected value, or if you like to call it, you can call it the mean, mu sub x, for x when we have a discrete random variable, is the summation of all the individual x's times all of their probabilities. So we talked about how to get that in the previous notes. You take each individual outcome, x, multiply it by its probability, and then you add that up for all of those products, and that gives you the mean, or the expected value, as some people call it. So now let's talk about the standard deviation of a discrete random variable. And this outline sort of looks like the table we looked at yesterday, right? On top we have the outcomes, and then on bottom we have the probabilities for each one. And then we start by finding the variance of a discrete random variable. And this formula is actually on the formula sheet too. So how do you calculate the variance and standard deviation of a discrete random variable? Okay, let's start with the variance. And it is important to point out this is for a discrete random variable. We'll look at a different kind of random variable in just a minute. So this is similar to what we learned in Chapter 2 with how to calculate variance. You're going to start by just subtracting the mean from each individual in the distribution. So the first person, x1, subtract the mean. The second person, we call them x2, subtract the mean. So you go through and subtract the mean from each individual in the distribution. So we look at how far each individual is from the mean, and then we square each of those differences. So if you look at the formula, subtract the mean, and then you square the difference for each one. So notice that turns it positive. So after we've squared the difference for each one of those differences, we multiply by the associated probability. So multiply each term by its associated probability. For example, the first outcome has probability P1. The second outcome has probability P2, and so on and so forth. And then last but not least, we add up all of these products, or we could say sum all of these products. That's what that big E sigma thing means, is to sum or add all these things up. So that's how we get the variance. And if you remember, the variance is a measure of spread. So how far each one of these things is from the mean. And then standard deviation, to get that, we just take the square root of the variance. So whatever our answer is for the variance, if you want to get the standard deviation, you just take the square root of it. And as far as the formula sheet goes, they only give you this piece about the variance. So knowing to take the square root of the variance to get the standard deviation is on you. The formula sheet just gives you this. Take each individual, subtract the mean, square it, multiply it by its probability, and then add them all up. And then how do we interpret the standard deviation in this case? Really similar to our interpretations of standard deviation in the past. We can just say it represents the average distance that the outcomes are from the mean. So on average, how far are these individuals typically falling from the mean? And make sure we add some context to that when we interpret. So should be no surprise there as to what standard deviation represents in this case. So example 1 says, use your calculator to calculate and interpret the standard deviation of x in the languages example. So I've brought back the data table from the languages example, and we already calculated the mean for this. So the expected value, or the mean, was 1.457 languages. So to get the standard deviation, we're going to start with the variance of x, which isn't just sigma, it's sigma squared. Okay, and let's start with 1. The first case, kid that speaks 1 languages, subtract the mean, square that difference, and then multiply it by its probability, which was 0.630. Okay, now we're going to add in the same thing for two languages. So start with 2, subtract the mean again, square that difference, and then multiply it by its probability, which was 0.295. And then let's go to 3 languages, subtract the mean, square it, multiply it by its probability. We'll do it for 4 and for 5 as well. And then we're going to add all these up to get our variance. So we can say the variance, sigma squared, is 0.450. And then we just have to keep in mind that the standard deviation is just sigma. So if the variance is sigma squared, we just have to take the square root of this answer to get our standard deviation. So the square root of 0.450 is 0.671, and the units here would be languages. Okay, so that's our standard deviation, right? That's our sigma x. So now let's go ahead and interpret this, the 0.671 languages piece. We can say the number of languages spoken by a randomly selected U.S. high school student. I think that's what the problem said, right? They randomly selected U.S. high school students. So the number of languages spoken by a randomly selected U.S. high school student typically varies by about 0.671 languages. It's like an average, right? So it's okay to be a decimal. It varies by about 0.671 languages from the mean number of languages, which was that number. Okay, so hopefully that makes sense to you. That's an example of when we would interpret standard deviation for a discrete random variable. The next part here says, are there any dangers to be aware of when using the calculator to find the mean and standard deviation of a discrete random variable? And if you want to see a calculator shortcut or tutorial, you can look on page 354, or if you look online, where our online textbook is at, you can look at the technology corner, number 11. So, I do, like, if you have to show your work for this, right, which you do for the AP exam and our tests, at least just show the first few terms, right? So you got to show some work. Don't just say the mean is blank, the standard deviation is blank. So you can show the first few terms. We've done this before for chi-square. Just show the first few terms, like that guy, that guy, that guy, and then just put dot, dot, dot. Right? As long as you demonstrate the pattern, that'll get you full credit for showing the work. So it should be relatively simple, and there have been questions just like this on the AP exam. But you do need to go ahead and illustrate your work, and you can do that. Just show the first few terms and put dot, 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 and then take the square root of your answer, and you're in business. So that's enough about discrete random variables. Let's talk about the other kind of random variable. There's only one other kind. It's continuous. So in italics here it says discrete random variables commonly arise from situations that involve counting something, things that are countable. Situations that involve measuring something often result in a continuous random variable. So in the green box here it says a continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve, like a normal curve, for example. The probability of any event is the area under the density curve and above the values of x that make up the event, basically above the x-axis and under the curve. Calculus people, that should sound familiar. So what is a continuous random variable? And let's give some examples here. So it's different than a discrete random variable. Continuous, you can never measure exactly or precisely what the values are perfectly. That's the point. So continuous means it's a measurement. We can never actually measure perfectly. We can never actually be exact. Whereas discrete, we just had some categories and we just counted things. So for discrete, we can easily count or identify specific values. So it has clear gaps. Things are fixed. 1 language, 2 languages, 3 languages, for example. So we're going to make some comparisons about things that might be continuous random variables and things that might be discrete random variables. So let's start with foot length versus shoe size. One of those is continuous, one of those is discrete. Keep in mind, things that are lengths, those are measurements. So this is going to be our continuous random variable. even if we have the best ruler in the world, we're still not going to be able to measure it perfectly exact. Whereas shoe size, we put people into categories, right? That's a discrete random variable. You're either a size 8, maybe 8.5, 9. So that would be a discrete random variable. But things that require measurement, those are continuous. How about your age, your exact age, I'm talking about like the minute and the second, versus how many birthdays you've had. So your exact age, again, that's something you would have to measure with, say, like a stopwatch, or you're watching a clock, which makes this continuous. It's hard to put your finger exactly how old you are at any given moment. Whereas the number of birthdays you had, that's pretty obvious, right? How old are you? That's the number of birthdays you've had. That would be a discrete random variable. Let's do one more here. How about your time in a hurdle race, if you run the hurdles, versus the number of hurdles that are out there on the track? Well, one of those things is countable, right? The number of hurdles on the track would be a countable thing. Whereas the time, and it's really tough to get that time exact. Maybe you go to 10 decimal places or 20 decimal places. So if you're measuring time, that's a continuous random variable. It's hard to tell the exact moment. And the number of hurdles on the track, that would be a discrete random variable. Hopefully you like my little hurdler here. So let's talk about the concept behind something being continuous versus something being discrete. The next question says, is it possible to have a shoe size of 8? Well, yeah, a lot of people have a shoe size of 8. So yeah, that's definitely possible. The next question, though, says, is it possible to have a foot length of exactly 8 inches? And I think scientifically we would argue that that's not possible. Think about when people measured lengths 100 years ago. They aren't nearly as precise as we are today. Whereas people 100 years from now would probably measure lengths and think that our stuff's old and outdated, and we were actually not that good at measuring lengths, say even down to, whatever decimal place. So you can never be exactly 8 inches. Even if you use a microscope or look at like the atomic level, we're always going to have some little bit of variability. So that's where this idea of a continuous distribution comes into play. And the better our instruments get as far as what we use to measure things, the more decimal places we can carry this out. But still, these decimal places could be infinite, right? So we can't ever actually measure it exactly to 8 inches. So that would be a continuous random variable. The discrete one would be people that wear a shoe size of 8. Sure, there's a lot of people that have slightly different size feet that all fit into a size 8 shoe. So then the next question asks, how many possible foot lengths are there then? How many possible foot lengths are there? And the answer is, if they can all be off by some really, really tiny decimal, that means there's an infinite number of foot lengths. Just like this decimal could go way out to infinity, there's an infinite number of foot lengths. Each one could just be slightly different than the other, down to like the 100th decimal place. So then the question is, how can we graph the distribution of foot lengths if there's an infinite number of them? Well, one thing we can say for sure, there's an infinite number of foot lengths. A histogram won't work in this case, right? Because we would have an infinite number of really, really skinny bars to try to represent each really, really tiny decimal. So instead of trying to represent these with a histogram, we use a density curve, like a normal distribution, for example. Notice it's a smooth density curve. So with discrete random variables, we could represent them with a histogram, but obviously that's not the case. That won't work for continuous random variables. So we can use a density curve, like a normal curve, for example. How do we actually find probabilities for a continuous random variable? Well, it's the area under the curve, and we did a lot of that within Chapter 2, whether it was a normal distribution or a uniform distribution. For example, I'm just going to draw a standard normal curve. So the mean is 0, standard deviation 1. This is where z-scores come from. So I'm going to put the mean at 0, and then I'm going to shade a portion of the curve, and I'll go ahead and tell you that's between 1.2 and 2.8. So what's the probability of a z-score being between 1.2 and 2.8? And remember, z-scores are just a measurement of standard deviation. How many standard deviations are we away from the mean? So for this portion right here, from from 1.2 to 2.8, it would be 0.1125. So you could use the normal CDF command, or you could use the chart for normal tables to find that. But the point is, this is just an interval from 1.2 to 2.8, and from that we can construct this little part right here and find the area of it. If you ask me to just draw a straight line, right, and I'll make a little dotted line here, that actually has no area. A straight line itself has no area. So the next part here says, for a continuous random variable x, how is the probability that x is less than a number, let's say a, related to the probability that x is less than or equal to that same number? So let's say, for example, this z-score is negative 0.78. What's the probability that z is equal to exactly negative 0.78? Well, if you remember, continuous random variables can't equal numbers exactly. And this line also has no area by itself, so the answer would be 0, because there's no actual area covered by a single line. We would need two lines and an interval to shade a piece of this graph. We don't have that here. So since continuous random variables can't equal a number exactly dead on like that, we can say that these two things, x less than a and x less than or equal to a, those two probabilities are the same. They're going to be the exact same. So whether you say x is less than a or x is less than or equal to a, those say the exact same thing. It's like trying to include the area of a line. It makes no difference. If you'll remember, that was actually a big distinction for the last section for discrete, but now there's no distinction at all. These are the exact same for continuous random variables. And the reason being is that the boundary line adds no area, right? A line, you can think of it as just being one-dimensional, and a line by itself actually has no area. So it's just lines marked on the curve. So to actually get a probability for a continuous distribution, the only way we can do that is to have intervals of values. That way we can go from one boundary line to another boundary line, and that'll actually give us a value for our probability. Okay, so let's illustrate that with this uniform distribution here. Uniform just means flat and same all the way across. The first question is, what's the probability x falls between 0.5 and 1? So here's the x-axis. It looks like it goes from 0 to 2. What's the probability it would fall between 0.5 and 1? Well, we can mark off 1 and 0.5 as our boundaries, and then you can start to see, make an area here. We shade this, it actually makes a square. So this shaded area represents the probability. So the key is, look at the x-axis, mark off 0.5, mark off 1, and try to find the area of this piece, which should be pretty simple to do here. I mean, it's a square, right? So from here to here is 0.5, the height's also 0.5, so the probability would just be 0.5 squared, or 0.25. The next question, and I guess this is sort of a trick question, what's the probability you get x equal to 1 exactly? And so if I make a dotted line here at 1, that dotted line itself has no area to measure. So if you ask me equal to 1, that's the probability is 0. This thing has no area. Similarly, what if I said, what's the probability, if I mark off 1.5, for example, what's the probability x equals 1.5? Well, again, this has no area. So this would be 0 also. It's a 0 probability. So the point being, anytime you have an exact value, probability x equals an exact value, and it's under a curve, the answer is going to be 0. We need an interval of values so we can start to construct this area. This is a really common type of question about continuous random variables. They'll give you something uniform and flat like this, and they'll ask you about the probability. You have to be able to mark off those boundaries and find the area between those boundaries. And usually it's just a square or a rectangle or something simple that you can find the area of. All right, the last example for these notes has to do with the weights of 3-year-old females. It says the weights of 3-year-old females closely follow a normal distribution with a mean of 30.7 pounds, and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. So this sounds like a normal distribution problem. Part A says find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. Well, this is a problem technically we should have been able to do after Chapter 2. I'm going to take the state, plan, do, conclude approach, starting with what is X? So X is the weight of a randomly chosen 3-year-old female, and we want to know what's the probability that X is greater than or equal to 30. Or if you just say greater than 30, that would be the same exact answer here. For the plan step, we're given that X is normally distributed. There's no condition to meet there. We're given that, and we're given the mean and the standard deviation. So for the do step, let's go ahead and illustrate this. Sketch a normal curve, put the mean smack dab in the middle, give it a label, and then we can mark off 30.7 because that's our probability. Excuse me, I mean 30, right? What's the probability that we get one bigger than 30? So mark off 30 and shade everything above it. Should be over half, by the way we shaded it, right? Should be over half. So you can use the normal chart, or I know a lot of people are fans of just using the calculator. So if you want to know this probability, we can use normal CDF. So we can say the command normal CDF. Our lower bound we marked off was 30. Our upper bound would be infinity, 1e99. And then we give the mean and the standard deviation, which gives us our probability, well, gives us our area of the curve of 0.577. Seems reasonable since it's over half. In the conclude step, what does that mean, that answer 0.577? So let's be really clear about this. There's about a 57.7% chance that a randomly selected 3-year-old female weighs at least 30 pounds. So to be really clear about that conclude step. All right, part B, what's the probability a randomly selected 3-year-old female just weighs between 25 and 30? So there's an interval of values. What's the probability we get X somewhere between 25 and 35? So again, let's illustrate the curve, same exact curve, right? I can copy and paste it. And now let's mark off 25 and 35 and shade everything in between there. So we've got the curve illustrated. That's part of our evidence when someone's grading our work. And then to find that probability, again, you can use the normal chart if you want to use z-scores, or just use the normal CDF command. The lower bound we marked off was 25. The upper bound was 35. Mean, standard deviation. And that gives us our area of 0.827, which in context, what does that value represent, that answer? Well, that means there's about an 82.7% chance that a randomly selected 3-year-old female will weigh between 25 and 35 pounds. All right, and then part C, this is the last kind of question that you'll see. I feel like A and B are a little bit easier. You could have done those in Chapter 2 before you knew what a random variable was, before you started labeling things with X. Part C is a little bit different in that it asks, if I tell you the probability that X is less than some number K is 0.8, what's the value of K? And this is the same scenario, by the way. We're still talking about the weights of 3-year-old females. So from what we've seen so far, K would be like our boundary line on the curve. So probability X is less than or equal to, or just less than, some weight, whatever K represents, there's an 80% chance. So 0.8 would be the area below that boundary line. So for K, we know 80% of weights, because that X would be the weights, 80% of weights are less than this value K. So it would be a major help if we could once more sketch this normal curve. We know the mean, we can label it, it's normal, mean, and standard deviation. If we could just sketch this one more time and try to estimate where we might mark this boundary such that 80% of the area is below it. So there's K, and and that should be in green here. This makes up 80% approximately of the curve, right? That's the green part there. So really we're working backwards at this point. There's the boundary. So where's that boundary at? So as far as finding position in a normal distribution, because this is a position, right? It's technically the 80th percentile. We can always use the z-score for 0.8, or you can use the inverse norm command in your calculator. So either use the z-score formula to solve for k or inverse norm. I'm a fan of the calculator myself, so if you tell your calculator to look for an area 0.8, that's the area below the boundary, the mean is 30.7, standard deviation is 3.6, it gives you 33.63. So hopefully you know the units and what that value represents. That means that 33.63 pounds is at the 80th percentile for this distribution, which is the weights of 3-year-old females. All right, so we talked about continuous distributions. We also talked a little bit about discrete random variables and how to find the standard deviation of those at the beginning of the notes. Anyway, that's all for these notes. I'll see you in class.